what I get on the right side. So when I divide this side by phi a times phi b, the phi b's cancel, and I get just phi a prime of x divided by phi a of x. So I have a very simple differential equation in x relating phi a and phi b. And this equation I can solve, right? We can solve it by integrating both sides with respect to x. And when I do that, the integral of phi b prime over phi b of x is just the log of phi b of x. And we can check that because the x derivative of this would just give me phi b in the denominator and phi b prime in the numerator. So that's the integral of this side of my equation. Must then equal, when I integrate this side of the equation, it's the same logic. That gives me phi a of x. But of course, remember, I'm integrating, so there's always this arbitrary integration constant plus c. So I've solved my differential equation. That was fairly straightforward. And now I can actually relate phi a and phi b. I can solve my result here by just simply exponentiating both sides of my equation. And the left side then tells me I get phi b is equal to just some constant, e to the c, where c was my original integration constant, times phi a of x. So these two pieces, the real and imaginary parts of my complex solution, are just related by a constant. So therefore, and now here we get to the conclusion. So phi n of x, which you may recall was originally phi a. Of course, all these functions are functions of x. I'm just getting a little tired of writing the function of x, plus I times phi b would equal phi a plus I, but phi b we see is e to the c times phi a. And all of this then can be factored as just some complex number, which happens to be 1 plus I times e to the c, multiplying then a real function, phi a of x. I know phi a of x is real because it's just the real part of phi n of x. And this is what we had set out to prove, right? That this bound state solution is really just a constant times a real function. And because the time-independent Schrödinger equation is a linear equation, we know that if this is a solution, then this thing related by a constant is also a solution. So therefore, phi n of x is just related to a constant times a real solution. So any solution to this equation can be thought of in this form of just some potentially complex number times a real solution. And that's one of the things we had set out to prove. So that we never really have to worry about that we would be missing out on anything by looking for complex solutions, right? In fact, if I hand you a complex solution for a bound state, now you should know immediately, well, that was kind of perverse, right? All he must have done was taken a nice real solution and multiplied it by a complex number. Very good. So that was one of the first things we wanted to prove about the reality of the solutions, of bound state solutions. And now we can turn to our next topic.